There is a question that comes up almost every time quantum computing gets discussed in public, and it is a completely natural one. People heard about personal computers in the 1970s and were told they would never leave the research lab. They heard about the internet in the 1980s and were told it was a tool for academics and the military. They heard about smartphones in the early 2000s and could not have imagined that within a decade, nearly every person on Earth would carry one. So when people hear about quantum computers today, the question that follows is almost inevitable. Will I ever have one in my home? Will quantum computers eventually become personal devices, the way classical computers did? It is a fascinating question, and it deserves a genuinely honest answer, one that takes both the physics and the engineering seriously, without defaulting either to breathless optimism or reflexive dismissal. Let us start with where quantum computers actually are today, physically and technically. The most advanced quantum computers in the world right now, machines built by IBM, Google, IonQ, and others, are not small. They are not even close to small. The superconducting quantum processors that IBM and Google use must be cooled to temperatures of around 15 millikelvin, which is roughly 100 times colder than the coldest known regions of deep space. Achieving and maintaining those temperatures requires a device called a dilution refrigerator, which is a large, expensive, and extraordinarily complex piece of equipment. A state-of-the-art dilution refrigerator can be taller than a person, costs hundreds of thousands to millions of dollars, consumes significant amounts of power, and requires highly trained specialists to operate and maintain. The quantum processor itself, the actual chip at the heart of the machine, might be smaller than your thumbnail, but everything required to keep it functioning takes up a room. This is not a design that fits in a living room, or a backpack, or anywhere near a typical household environment. Beyond the refrigeration challenge, there is the problem of isolation. Qubits are extraordinarily sensitive to any form of environmental disturbance. Vibrations, electromagnetic interference, thermal noise, stray magnetic fields, any of these can cause decoherence and destroy the quantum state that the computation depends on. Quantum computers today are housed in carefully engineered, shielded environments, specifically designed to minimize all of these disturbances. A home environment filled with Wi-Fi signals, appliance motors, passing traffic, and the general electromagnetic noise of modern life would be extraordinarily hostile to a qubit, trying to maintain coherence. The engineering required to isolate a quantum processor sufficiently in an ordinary home setting does not currently exist and would represent a profound technological challenge even to attempt. So the honest, near-term answer to the question is no. In the next 10 to 20 years, you are almost certainly not going to have a quantum computer sitting next to your router. The physics and engineering barriers are simply too large. But here is where the conversation gets more interesting, because the question of whether you will ever access quantum computing from your home is a very different question from whether you will ever own one. And the answer to that second question is already, in a limited sense, yes. IBM has operated a cloud-accessible quantum computing platform called IBM Quantum, previously known as the IBM Quantum Experience, since 2016. Through a browser interface, anyone with an internet connection can write quantum programs, submit them to real quantum processors, and receive results. Researchers, students, developers, and curious members of the public have collectively run hundreds of billions of quantum circuits on these cloud-connected machines. This cloud model is almost certainly the primary way that most people will access quantum computing for the foreseeable future. Not through a device in their home, but through a quantum processor in a data center, accessed remotely over the internet. In much the same way that you access enormous classical computing resources today, through cloud services like Amazon Web Services or Google Cloud, your laptop does not contain a supercomputer, but it can access one. The same principle applies to quantum computing, and the infrastructure for this model is already being built. Now, could the hardware itself ever become compact enough for home use? This requires looking at alternative approaches to building quantum computers, because superconducting qubits are not the only game in town. Photonic quantum computing, which uses particles of light, photons, as qubits, can in principle operate at room temperature. Photons do not need to be cooled to near absolute zero because they do not interact strongly with their thermal environment in the same way that superconducting circuits do. Companies like PsiQuantum and Xanadu are pursuing photonic approaches, and if this technology matures, it could potentially lead to quantum processors that are far more compact and do not require dilution refrigerators. However, photonic quantum computing faces its own substantial engineering challenges, particularly around generating and detecting single photons reliably, creating the entanglement and nonlinearity needed for universal quantum computation, and achieving error rates low enough to be useful. Room temperature operation does not automatically mean consumer-ready hardware, and none of the leading photonic approaches are close to delivering a practical, scalable quantum computer yet. There is also a category of device worth mentioning, called a quantum annealer, most famously produced by a Canadian company called D-Wave. Quantum annealers use quantum effects to solve a specific class of optimization problems and are not general-purpose quantum computers in the full sense. D-Wave's machines still require significant cooling and infrastructure, though less extreme than superconducting gate-based systems. They are not home devices, and their computational scope is narrowly defined. There is one more thing worth saying honestly, and it is perhaps the most important point of all. Even if the engineering was solved tomorrow and quantum computers could somehow be made room temperature, compact, and affordable, the question of whether you would want one at home is a different matter entirely. Quantum computers are not better at the things that personal computers are used for every day. They will not make your web browser faster. They will not improve your video calls. They will not run your spreadsheets or your word processor more efficiently. The problems where quantum computers offer potential advantages are highly specific: molecular simulation, certain optimization tasks, cryptographic applications. And most of those problems are not ones that individuals need to solve at home. The personal computer became a household device because it was genuinely useful to individuals for tasks they performed every day. Quantum computers, even in their most mature imagined form, are likely to remain tools for research institutions, pharmaceutical companies, financial firms, government agencies, and technology companies, accessed remotely by individuals and organizations that need their specific capabilities. The honest answer, then, is this: a quantum computer in your home, in the traditional sense of a physical device sitting in your house and owned by you, is not a realistic prospect for the foreseeable future, and may never be a realistic prospect given the fundamental nature of what quantum computers are and what they are good for. But quantum computing accessible from your home, through cloud interfaces, through applications built on top of quantum processors, through services that quietly use quantum resources on the back end, is not only possible, but is already beginning. The future of quantum computing for most people is not a device, it is a service. And that future is closer than most people realize.